In our last video, we talked about conservation of momentum and how to use that for our rigid bodies. And much like we had in our particles, when we talked about our conservation of momentum, we looked at a lot of special cases of impact, right? And so those were looking at our coefficient of restitution when we have bodies that are impacting on each other and then bouncing away. You're bouncing in the same direction, bouncing in different directions. We had oblique impact, we had central impact. And we had looked at those different kinds of impact for particles. But now we're going to look at what does impact look like for rigid bodies. And so with that, it's largely going to be very similar. We're still going to be able to use our coefficient of restitution when we have one body that may just be sitting there. Maybe it's pinned to something at the top, and then another body that chooses to come and strike it at some angle. So with our impact problems, we can still use that coefficient of restitution that we were using, which was our E value. E is that coefficient of restitution that is valid for values from 0 to 1, where we had VB2 minus VA2 over VA1 minus VB1. So those are your final velocities for your shapes A and B over your initial velocities for your shapes A and B, your two separate bodies that are impacting together and then bouncing off each other in some way. And these get used in combination with that conservation of angular momentum. Right, that summation of all of your initial angular momentums equaling the summation of all of your final angular momentums. And again, those are just right before and right after impact. They are just in those milliseconds of right before the hit and right after the hit are the velocities and angular velocities that we're looking at in these problems. So most of the time what we want to do is draw what it looks like before impact, what it looks like after impact for our kinematic diagrams, right? What are the velocities? What are angular velocities? And then use this combination of equations to go ahead and solve for any unknowns that we're looking for, which again are typically velocities and angular velocities in these cases. So we'll look at just one example problem here and kind of see how this works. So in this problem, we've got a 10-pound slender rod shown that's suspended from the pin at A and is initially at rest. If a 2-pound ball is thrown at the rod and strikes its center with a velocity of 30 feet per second as shown, determine the angular velocity of the rod just after impact. Coefficient of restitution is E equals 0.4. Now, if you watched the last video where we talked about conservation of momentum, you might think, oh, this looks pretty similar to that, right? We had a rod that was hanging from a pin and a bullet was striking it at an angle. And the difference with that problem is that our bullet was becoming embedded in it, right? So now instead, in this baseball problem, we have this ball that is hitting the rod and then bouncing off, right? They're not becoming intertwined together. They're not moving together. They're going to bounce off and have different velocities afterwards, which is determined somewhat by that coefficient of restitution. So that coefficient of restitution is really a big flag that, hey, we've got this impact problem. We're going to have to use this E value to relate the velocities of this ball and this rod together. So let's break it down and look at this before and after. Okay, so in our before, if we draw a kinematic diagram for the before, we have a rod that is just hanging out here in space. This rod is just at rest, nothing really going on with it, until this baseball comes along, and really like the before is just before impact. He's right about to touch it. He's right up on there. He has this, his mass times his initial velocity. So I'm actually going to call this, maybe I'll put it like right through the middle there. Mass of ball times velocity of ball initial. And we know what that initial velocity of that ball is. It's 30. And we do know the mass of that ball. Right? They said it's a 2-pound ball, so we can divide that by our 32.2 and find the mass. And so we have a pretty good picture of what the before is. We know all our velocities, we know pretty much everything that's happening. It's our after that we're trying to figure out. So if we look at our after, and I draw again my rod, my rod is now moving, right? That ball is pressed up against it and then is going its own way, right? So now this rod has a velocity, and because it's fixed at the top up here, has an angular velocity as well. It's rotating around that fixed axis. So we've got that rotation about a fixed axis, I-O omega, and the rod has a velocity, right? This mass of the rod times the velocity of the rod. We'll say velocity of the rod 2 for the final velocity of that rod there. But we don't want to forget about the baseball. That's still a part of this system, right? It's impacted and then now it's going its own way. And I'm not sure if this baseball is going to either like bounce back and move backwards, or if it's going to keep swinging in line with the rod. So I'm just going to assume for now that it just keeps moving forward, where we have the mass of our ball times the velocity of the ball, the final velocity of that ball. And if I assume the wrong velocity direction, that's okay. It'll work out in the math, right? If I get a negative sign for my VB2, it just means that my velocity is negative there. So with that, we have an idea of what our velocities are, what our momentums are for this impact problem. We know we've got an impact problem, so we know we're going to use our conservation of angular momentum, as well as that coefficient of restitution to figure out this angular velocity just after impact that we're looking for. So I'm going to write out both of those equations here. We're trying to find the sum of all of our initial angular velocities, so that's from our before. And then we'll pull our final angular, not velocities, our final angular momentum. Initial angular momentums and final angular momentums. Pull those from our diagrams here. And then we're also going to use our coefficient of restitution, VB2 minus VR2 over VR1 minus VB1. So before we get into that, let's go ahead and determine what all we know. What do we have in this angular momentum, this conservation of angular momentum? So initially, in our before, we only have the baseball that's moving. And since this problem is rotation about a fixed axis, I'm going to use my distance to that fixed axis, that O, I guess it's labeled A in this one, this A that's up here. I'm going to use that as my reference point for all of our angular momentum. So taking my angular momentum about that rotational point, about that fixed axis up there, my angular momentum is R times M times V, radius times mass times velocity. So in this case, I'm going to have RB, that's the distance from A to B, RB, MB, VB1. That's it. Those are the only things causing any momentum in the system in the before. And then we'll take a look at everything that's causing momentum in the system in the after. So that's going to be RB again, MB again, but now VB2, the final velocity of that ball. Plus, same for our rod, right? The radius of the rod, or not the radius of the rod, but the distance from A to the center of the rod there, times the mass of the rod, times the final velocity of our rod. And then, of course, we're going to have that angular velocity component too. We have that moment of inertia I about our fixed axis times omega, that angular velocity that we're looking for. All right, so with all of that in mind, let's go ahead and see if we can plug some numbers in, simplify this down just a little bit. We know our RB, that's going to be our distance, 1.5 meters, to where the ball is striking that rod. We've got 1.5 times the mass of the ball, which we had was 2 pounds. 2 pounds is our weight. 2 over 32.2 to get our mass. And then VB1, which they did give us, I believe. Yes, we have 30 feet per second. 30 feet per second. That's perfect. We know everything in the before, just numbers, plug them all in. Now we'll kind of look at our after, and this is where we've got a lot more of those unknowns. So our RB is still the same. It's still 1.5, and the mass of the ball is still the same. It hasn't changed. 2 over 32.2. But we don't know what VB2 is. Don't know what that final velocity of that ball is. Then we can move on to our rod. And the mass of our rod happens at the center of the rod there. Again, another 1.5 feet. So 1.5 times the mass of the rod. It told us 10 pounds for that slender rod. So that's going to give us 10 over 32.2. And then we don't know what the velocity of the rod is, so we'll just leave it as VR2. Plus our moment of inertia times omega. So our moment of inertia when we have a slender rod that rotates about its end, that's 1/12 ml squared. I'm going to plug in here 1/12 the mass of the rod. Since this is just the rod is the only thing that has that angular velocity. The ball does not get any angular velocity. Only the rod has angular velocity. So 10 over 32.2 times the length of that rod, which is 3 feet squared, times omega. Right, so we got all the little pieces in there. The only thing that we don't know is we don't know how to relate VB2, VR2, and omega. Right, we have 3 unknowns in here, and so we need to find some way to relate all of those things. And thankfully, we know that we have this coefficient of restitution that they gave us here of 0.4. And we know E is 0.4, so that's super handy. That can give us a relationship between our ball and our rod, like those final velocities. So if we plug that in here, 0.4 equals VB2 minus VR2 over VR1, which we know the initial velocity of the rod. It's not moving. It's just 0. And then minus VB1, that initial velocity of the ball, that's going to be 30. So it's minus that 30. So then I can multiply that over. I can get this relationship of negative 12 equals VB2 minus VR2. And then I think I'm going to solve this one for my ball. I'm going to go ahead and substitute in for VB2 in this relationship. And I know you might be like, well, why does it matter? Does it matter if I sub in the VB or the VR? And the answer is it does. It does matter. Because I can't get a relationship between omega and VB2. Like, it's just not possible for us for our kinematics. But if I go back to my kinematics, I can get a relationship between the velocity of the rod and the omega of the rod. Because I've got this lovely rotation about a fixed axis here, I can use this R and say V equals omega times R. And that relationship only works for everything that's internal to the rod. I can't relate it to the ball. So I need to get rid of that ball aspect, put it into rod, and then finish out our problem here. Right, so my VR2 equals omega times R. For here I'm going to have VR2 equals 1.5 omega. So that's why down here I want to have VB2 substituted in there. So VB2 is going to be VR2 minus 12. Right, just kind of swapping those, swapping this VR, adding this my goodness, sorry, my words are trapped in my mouth. I want to just add this VR2 to the other side, so that way I can solve for VB2, and I can do this substitution in here. And then I can also do this substitution at the same time. I can do this VR2 equals 1.5 omega, because my goal is I want to find that omega. I want to find that angular velocity. So I can substitute in for VR2 1.5 omega. Here it is again, 1.5 omega. So if I do that, let me write all of this out. I'm gonna simplify things a little bit to kind of help keep things straight. So for example, one thing I can do to simplify is I see that every single term is over 32.2. So I'm just gonna cancel all of those out. Right? If I just multiply everything by 32.2, it disappears on both sides of my equation here. And so then I'm going to simplify this. 1.5 times 2 times 30, that gives me 90. And then looking at my next one, I have 1.5 times 2 times VB2. That equals 1.5 times 2 is 3. And then we said VB2 becomes 1.5 omega minus 12. So that's going to get plugged in here. 1.5 omega minus 12. Then my next term, I have 1.5 times 10 times 1.5 omega, substituting that in for VR2. And so when I plug that in, I get, let's see, 1.5 times 1.5 is, don't have that written down on my paper, but it's 2.25, I want to say. I'm gonna plug it in my calculator real quick. Let's see how good I did. Not so good at the fractions, the decimals, multiple. Yeah, 2.25, perfect. All right, 2.25 times 10, so that's plus 22.5 omega. And then my last term here, I've got 10 over 12 times 9, and that one I did write down, that one is 7.5, plus 7.5 omega. So now I have everything in terms of my omegas. It's just a matter of doing that algebra here so that we can solve for what our angular velocity is. And so when I simplify this out and I get my angular velocity, I'm going to get 3.65 radians per second. 3.65 radians per second. And I can go back and I can solve for what these individual velocities of the ball and of the rod are. I didn't necessarily need to since the question didn't ask me to, but if I wanted to, I can just go back and plug those in and figure out if I was right, if I assumed the correct directions on these things. Right? So if I get positive answers, it means I assume the correct directions in my diagrams up here. If I get negatives, it just means that they're going the other way. So with these impact problems, just know you're going to have to use a combination of not only your conservation of angular momentum and your coefficient of restitution equation that has come back, but also any kinematics that you may need, like we did here with our rotation about a fixed axis to find that V and omega were related with V equals omega R.